In this episode, we will add tactile feedback to our various interactables. Switches will finish their rotation to either the fully upright or fully pulled position within a certain threshold. Wheels will have a slight kickback when the player lets go of them, as if the wheel is working on a ratchet and pawl system. And probably the most requested feature of this controller, we will be simulating adding weight and inertia to our doors. Welcome back. As you can tell from the intro, we are going to be doing a lot of cool stuff in this episode. However, we do need to bang out some bug fixes real quick. So let's fly through those, talk about what caused them and how we can fix them. All right, so the first bug fix I'm going to show you is over here with the switch. So as you can see here, I imported the Blender Monkey Suzanne. And what I want to do is I want to pull this switch down and I want to delete the monkey head. And the reason I want to do that is I want to simulate maybe when you pull the switch down in your game, you wanted a door to open so the player could go on to the next level. That may have been a problem if you've tried it yet. So let's go ahead and pull the switch down and you'll see we run into an exception. Now, what's happening here is I created this test script and this sits on the monkey head. And as you can see, if the switch gets above 80%, it's going to try to delete itself. This is a problem because if we look at our podium switch, grab our interaction component, once the monkey head is gone, there is no node to be calling execute on. So therefore, we have a null reference exception essentially happening. Now, luckily for us, this is a very simple fix. We just need to check if node and, because remember, this is just saying if the node is not null. So if the node is not null, then we can go ahead and check if it has an execute method. So let's go ahead and run our game, run over to our switch, pull it down, and you'll see the monkey head disappears. Now, you may have also noticed our second bug with the switch. If I look at the switch here and then look off, it looks like the reticle's not working. So what's actually happening here? So we'll look at the code in a second, but you can see here, I look at my switch and we call focus, which should change the reticle. At which point I now leave the switch, but we're not calling unfocus. So if we look at our interaction controller, come down here, you can see here our potential object was the switch. It has an interaction component and we're allowed to interact with it. So we focused. So then on the next frame, we had a current object and we continued to look at the switch. However, there was a frame there when we left the switch and began just to look at the podium. So the podium is a potential object because our interaction raycast collides with it. We can hit it. The player can't walk through it. So we have a potential object, but that potential object doesn't have an interaction component. So on this if check here, it doesn't have an interaction component, so it didn't do anything. You can see down here, we are missing an else block right here. What do we do when we collide with an object now that doesn't have an interaction component? Well, that's the same thing as looking at something we don't want to interact with. So what are we going to do? We're also going to unfocus in that case. So if I go ahead and hit start, I run over to my switch, my reticle changes, and as I look away at something I can't interact with, it changes back. So a little simple fix for the reticle. All right, our next bug actually sits on the wheel. So I've added some print statements into our code, and I'll go ahead and zoom in on them in the bottom left. So now as I rotate the wheel, you see we have a visible wheel rotation and we have the internal wheel rotation. Now you'll see this again in the code, but that wheel rotation we calculate ourselves and then we apply it to the actual object reference rotation Z. So if our wheel can spin a full 360 degrees, our visible wheel rotation is 360, but our internal wheel rotation should stop somewhere around 70. Now, if I keep spinning as if the wheel was moving, that number for the internal wheel just goes up and up and up and up, but nothing's happening to the visible wheel. Now, if I start spinning back, the wheel's not turning in the opposite direction, but the internal wheel rotation is lowering. So essentially, you have to go all the way around however many times you overturned the wheel to get back to where it was. And this is actually a very simple fix as well. In our code here, you can see that we're calculating this wheel rotation here and then applying it to the actual object reference rotation. And we're clamping the object reference rotation, but we're not clamping the wheel rotation. So we need to add a little bit of logic to get these to match up. So I'm just going to add it right here before my print statements. We're going to need 2 new variables before we clamp, and I'll explain why after I write them. So we need a variable that we're going to call min wheel rotation, and that is equal to our starting rotation, which once again we define at the start of interaction, and we're going to divide that by 0.1. We also want to statically type this to make sure that it's a float, and we're going to copy and paste this and change min to max and starting rotation to maximum rotation. Now, why do we need to divide by 0.1 here? And it has to do with this line right here. So the wheel rotation is defined by how far our mouse is moving clockwise or counterclockwise. And then we're applying that rotation to the object reference rotation, but we're adding this little multiplier here so that way the wheel doesn't spin too fast or too slow. To keep the internal wheel rotation in line with the visible one, we need to do this same calculation, but in reverse. And that's what we're actually going to apply to our clamp. Next line we've written 100 times, so I'm just going to go ahead and copy and paste it and go ahead and hit Control-C, Control-V to clamp. And this time we are clamping the wheel between its current value, and we want to clamp it between the min wheel rotation and the max wheel rotation. So if you kind of look at these two clamps, you'll see what they're doing. So the starting rotation and the max rotation, which we define here in the ready function, these are the object references kind of measurement for its rotation. So we need to clamp between these. However, the wheel rotation here is something we're doing on our own, and we're saying that maybe one knock of the wheel, one turn of the wheel is 0.1 of the object reference rotation. So when we do the clamp, we have to make sure that we're in the same kind of measurement, right? So let's go ahead and run this and see if it solves our problem. So here over at our wheel, I'll click and I'll turn it all the way. And you can see that the visible wheel rotation stays at 360 and the internal wheel rotation stays at 62. And if I go all the way back, you can see they both stick at 0. So as we increase the internal wheel rotation, the visible wheel rotation should increase as well, and vice versa, but we've now locked it and prevented overspinning from happening. So there's another bug fixed. All right, our next bug comes with our door. So here you can see our door interaction component, we're setting its max rotation to 90. Let's go ahead and set this to 180 and run the game. So if we go ahead and come over to the door here and I try to open it to a full 180, you'll see that it jerks back to the front. And as I continue to move my mouse up, it'll never stop at that high value. So what's going on here? Well, let's look at the door in 3D to see what's going wrong. So here in the door, I'm going to grab the pivot point because remember, this is what we're rotating on. And we're slowly rotating in the Y axis. And as we rotate, you can see that Y value in the transform over there on the right of the screen is going to go up and down. But you'll notice as I get close to 180 degrees, it'll actually go negative, positive, negative, and come all the way back around to 0. And the reason for this is Godot and most 3D engines don't define this movement as a measurement between 0 and 360 degrees. They define it as a measurement between minus pi and pi. And the reason for that is that's how it's measured in radians. And so that negative value that we're going to get here, while technically a valid value for the engine, is going to mess up our clamp. Because remember, if something is going to be lower than 0, we want it to stay at 0. We don't want to pull it any further forward. But that works in this negative value. It does not work in this negative value. So let's go ahead and go into the code and talk about how we're going to fix this. So back here in our code, in our input, in our interaction door logic, you can see here we're clamping that rotation. And like I said, when that rotation becomes negative, so negative 179 degrees, it's clamping down to 0. And that's actually sending it all the way back to the start. So we're going to need to kind of modulate this into our own measurement of the door angle. And to do that, we need to add a new variable. So up here at the top, we're going to add a variable, and this is going to be the door angle, which is going to be a float. And by default, we're just going to keep it at 0, 0. So then let's go ahead and scroll down, come back to our door logic. Now, right here, this event relative y times 0.001, this is the measurement of our mouse movement up and down. And so we're going to store this in a variable that I'm going to call delta. Delta meaning the change in our y value, essentially. We want to go ahead and change that right there. So now that we have this delta, we can actually just add this to our door angle to keep track of how much we've moved up and down, right? So our door angle is going to be plus or equal to delta. So as we push forward, the delta will increase and the door angle will increase. And as we decrease delta, as that gets lower, we decrease the door angle and the door will shut. Now we take this, we say our door angle is going to be clamped between our current value and our starting rotation and our maximum rotation. And then instead of clamping this value, we're just going to set this equal to the door angle. Now, if this seems confusing, I'm sure it does. All we're doing is calculating the angle ourselves and applying it to that rotation instead of giving Godot the values and having Godot calculate it, because Godot will throw in those negative values. Now, there is one thing we need to check. We also need to make sure that the delta is being applied correctly. And that is because if you remember, we have if is front here. This decides if we're looking at the front of the door or the back of the door. If we're looking at the back of the door, we actually need delta to be negative. So if it is the front, delta can stay positive. Else, if it's not the front, we need to say that delta equals negative delta, and that should reverse it. So let's go ahead and test this and see if it works. All right, so let's go ahead and run over here to our door. I push forward and it gets clamped. It doesn't jerk back to 0. And let's also make sure this works in the other way. I'm pulling the door all the way open and it's stuck there. So there we go. We have now fixed our door logic. And just to show you that this works for virtually any rotation, let's go ahead and just change this rotation to 720. I don't believe you would ever want a door to open this much, but we're going to make it go around twice. So we go, oops, we have to, in 3D, go to our sandbox because I made our door local in here. That's why we need to do 720 on this door. Go ahead and hit start. Now it'll go around once, twice. And there we go. We now have our door logic working as expected. All right, in terms of bug fixes, last but not least, we are going to talk about our interactable objects. So you can see here, if I pick up this green box here, and let's say I'm running with it, I want to take it into another room. If it gets caught on this wall here, I can get very far away from this box. I can be on the other side of the map and still have this box come flying towards me. So I think we definitely need to add in some limits to how far you can carry a box. So this is probably going to be our most simple bug fix of them all. Here in our interaction controller, we want to know if we're interacting with an object and if we're too far away. So here, if on the previous frame we are interacting with an object, we want to check if in this frame, if we've gotten too far away to continue interacting with it. And the way we're going to check that is we're just going to add another if statement here. And in this if statement, we're just going to check if the player camera, if its global position, we're going to check its distance to the current object's global position. And then we need some value. I'm going to say 3 meters or so. I think that's probably fine. And so if it's gotten to that point, we also need to make sure we still have an interaction component. And if we are going to drop the object, we need to make sure we're running the post interact on it, because even though we didn't choose to stop interacting with this object, we still want any post interact logic to fire. We need to set our current object to null because we are no longer interacting. And then we need to unfocus. So we're taking where our player's camera is and finding out how far we are from the current object. And I'm just doing 3 meters, depending on what game you want. You could probably change that value. And if that's the case, we want to post interact and no longer interact with the object. So let's go ahead and test to see if this works. So just to show you, I'll pick up my big heavy object. And if I back up, I drop it. So now if this is some big, heavy, important object, I'm probably going to want to be very careful moving it. And just to show you this also works with it getting caught on walls, let's go ahead and put him on the wall here. And yeah, you can see he immediately goes. So 3 meters might be a little too close to be dropping items, but I think it feels good for my game. I'll let you guys decide what you want to do for yours. So those are the major bugs I wanted to tackle in this episode, specifically the ones I wanted to talk about and explain why they were happening and how to fix them. Let's go ahead and talk about some more fun stuff, new additions, and things we can change to improve our game. So in the previous episode, we added an outline shader to collectible items. So if you were in a dark, spooky environment, and maybe there was a health pack on the floor, you kind of wanted to show the player it was there, even if they didn't have any flashlight, battery, or something of that nature. So we added that little blue outline that you see on the items that pulses. Now, this was a simple addition, something I came up with on my own, and while perusing the Godot shader website, I discovered a item highlighter that kind of coincides more with the AAA game style of doing it. And I actually really like this, so I'm going to show you how you can swap out shaders pretty easily and the improvement that you can make to your visuals. So I'll leave a link in the description below, or I'll pin a comment to the shader. If we go into our item and into our mesh instance 3D, you can see our surface material override. We just have a gray color on it, right? So we want to do this in the same way we did the previous shader. We want to do a next pass, and we want to do a new shader material. And on this new shader material, we need a new shader. And so we're going to go ahead and call this item highlighter shader, and we're going to drop this in our shader folder. All right, so I'm not going to make any changes to this shader, so just go ahead and copy, paste, and drop it in. And then we can go ahead and zoom in. So as you can see, it's got that white bar that kind of shimmers across it. Let's go ahead and look in the shader parameters. I think I want the speed to be a little bit slower, so maybe 1. Yeah, I think that looks much better. Let's go ahead and make sure it's happening at least a little bit more frequently. So like 3. Yeah, that looks good. I think that'll stick out a lot to the player. So let's go ahead and save this material. And the way we're going to do that is we're going to right click on the next pass, and we're going to click Save As, and we're going to put this in our materials folder and call it Item Highlighter. And make sure that you clear it from your item by default, because remember, we are applying and unapplying this dynamically in the code. So in your materials folder, you should have that resource. So if we go ahead and hit save, if we go into our interaction controller script and go to the top, you'll see that we had this outline material that was our previous outline resource. Very simply, all we have to do is change this to the item highlighter. So if I walk over to the objects, you'll now see that they get that shimmer applied. So you can imagine if this was a very dark environment, how nice this would look as opposed to just some random blue highlight. All right, now it's time to add some tactile feedback to our objects. And what I mean by tactile is, the biggest comment I've gotten so far, or biggest critique I should say, is that switches, the doors, the wheels, they don't feel real. It really feels like you're playing a game, which kind of defeats the main purpose of an immersive sim controller. I think the easiest one to start with is going to be the switch. All right, so to improve our switch movement, we are going to need to add a few variables. We are going to call these our switch variables, just so they kind of stick out to us. We need a switch, and we're going to call this the target rotation. We need the lerp speed. And this is also going to be a float. Let's make this 8.0. And let's also add a variable called is switch snapping. This is going to be a Boolean, and it's going to be false for now. So as we write our logic, we'll talk about these variables and what they do a little more in depth, but you will at least recognize the lerp from lerp speed if you watched all the way back at the very beginning when we were talking about camera movement and, regular movement as well. We want to animate the switch and make sure everything is happening nice and smooth, and this lerp speed is going to define how smooth that actually is. The target rotation is going to hold the value we want to be lerping and animating to. And is switch snapping is just a Boolean that explains exactly what it does. So the first thing we need to do is go ahead and come down here and add something right after our pre-interact. We need to add our process function. Now, we don't have our process function yet because typically we don't want something happening every frame regardless of what we're doing. However, we now need to add the process function because what'll happen is we'll stop interacting with the switch and it may need to finish out that last little half rotation or whatever it is to complete the switch. So essentially the object is going to have to do a little bit of action when we let go given some circumstances. And this will be the same for all of the three objects that we're interacting with. And so let's go ahead and add our interaction switch statement, or in the case of Godot, a match statement. So we want to know what our interaction type is, and we have a few. Let's just go ahead and grab these here. So if it's the door, we want to return. If it's the wheel, we want to return as well. And if it's the switch, we're going to want to do some logic. I think it'll make more sense if we go ahead and hit return and decide when we are going to snap the switch to the top or the bottom. So back here in 3D, if you imagine this little turn right here, that's probably 5% switched. We want that to go back to the top, right? If I let go here, we want it to go back up, and then same down here. This is fully completed. If it's right here, we want it to snap down. So if you got to think, we want to do it at the top, so maybe 20% or less, and at the bottom, maybe 80% or more. And we only care when we let go of the switch, right? We don't want it moving when we're interacting. We want it to happen right as we let go, which of course is going to happen in our post-interact. So in our post-interact, we're going to have to add a switch statement or a match statement as well. And this is going to have to happen for all three of our interactables. We still want to say we're not interacting, and we still want to lock the camera, and we still want to affect the mouse mode. But if we have just finished interacting with the switch, what do we want to do? Well, we need to get the percentage that the switch is at. So where is the switch currently at? And this logic is something we've already built. This is the percentage calculation we have right here. So go ahead and copy your percentage calculation and bring it right here. So that way we have percentage, although it's not defined. So we need to say var percentage, which is now a float, or it's always been a float, but we need to specify it's a float. And that percentage, we're going to say if percentage is less than, I think 0.2, we'll say 20%. Although I think for the sake of the tutorial, I'm going to make it 0.3. So when I demonstrate this, it's clear and obvious. And then we could also check if the percentage is greater than 0.7. And so if these two are true, we're going to want to say we want to snap the switch. So we'll say is switch snapping to be true. And we want this for the bottom one as well. So if we pull the switch maybe halfway down, we don't want to snap it anywhere because then that could be pretty confusing for the player. Or maybe for your game you do, in which case you want to modify these values. But the big kicker here is we need to set our target rotation, what we actually want it to be. And so if it's less than 30%, we want to put it back to the start, which means we want to set our target rotation to our starting rotation. And you may have already guessed that we want the opposite. If we are almost done, we want our maximum rotation. So essentially, when we let go of the switch, if we are too close to the start or too close to the end, we want to send it all the way back or complete the cycle entirely. So how are we actually going to do this? So that's what we needed our process function for. So up here, we need to check if is switch snapping, which means that this will run every frame, but we will only do something to this switch if we have set the is switch snapping to true, which can only happen if we've interacted with it in this specific instance. So if the switch is going to snap, let's think about what we need to do. Well, we're going to need to move the switch. So let's go ahead and go down to our input. And you can see here, we have our clamp. So I'm just going to go ahead and copy this and put it up here. Now we're not going to clamp, but we are going to set the rotation. So instead of clamping it between these two values, we're going to lerp from our Z rotation. We're going to lerp towards our switch target rotation. And we are going to do that at what speed, which is going to be delta. This is the time between frames. And we want to do it times the lerp speed we defined before. So what exactly are we doing here? So this object rotation of Z is going to be a value, let's say 0.75. Let me go ahead and run the game. If this value is at 0.75, say right there, we want it to push down. So if this is 0.75, the switch target rotation was just defined in the post interact as being the max rotation, so 100%. And how fast are we going to do it? We're going to do it times the lerp speed we defined, and delta just ensures that this is frame rate independent, so if there's a lag spike, nothing bad is going to happen. And so obviously at some point we need to decide to stop snapping, and instead we need to kind of reset things back the way they were. So the first thing we're going to do is we're going to check if the absolute value of our object rotation of Z minus our switch target rotation is less than 0.01. So why are we doing this? Hey everyone, future me, just stopping in to say that was about to be a long-winded explanation that I don't think really did lerp justice, so we're going to do a quick interjection to explain why we need that threshold and talk about what lerp is actually doing. So if you imagine we have this goal here, so this is our start and this is our end. So lerp is essentially a way of animating dynamically through code where we go from the start to the end, right? So here on frame 1, our switch would be at whatever rotation it's at. Then on the next frame, it's going to be right here, and then on the next frame, it's going to be right here, and then on the next frame, it's going to be right here, right? And the distance between these is determined by that lerp speed times delta value, right? However, with lerping, the problem is going to arise where eventually you go here and then here, and you just keep getting closer and closer to the end, but you may not actually get there. So if you imagine that the end is 100%, you'll be at 99, then you'll be at 99.9, then you'll be at 99.99. So you'll always be approaching 100. You'll be approaching the limit of 100, but you won't actually hit it, which essentially means if we did not add in this absolute value threshold, this switch would always be moving and the process function would be doing a constant calculation, which is not a good thing if you have a game with a lot of switches in it. So essentially, when we created that threshold that is 0, 1, we're saying, well, once it gets to this value, it's close enough for us, or actually, I think it might be this value. It's close enough for us to say, you know what, it's done, it's at 100%. So what we're going to do is we're going to arbitrarily set it at 100%. And to the naked human eye, you would have no idea that the animation stopped. So at this point, we've decided that the switch is close enough to either the start or the end after moving. So what do we want to do? Well, we want to go ahead and just take the rotation and manually set it the last little bit. So at this point, it's already animated, to decimals and decimals of closeness. The average user isn't going to be able to tell when we just hard set it to that value. And then once it's at its final spot, we just want to say, is switch snapping false? Because now we don't want to be lerping this anymore. We want the player to have to re-interact with the switch to do any kind of more logic. And then finally, we also need to update the percentage again because we want the percentage to be accurate. So I'm going to scroll down to my switch and I'm going to grab these two lines. I'm going to scroll back up, and outside of that if statement, we want percentage and notify. And the reason is we still want certain things to happen based on percentages. And once again, we need to say that percentage is a float with this calculation. And we still want to notify the various nodes that are affected by the switch to have the correct percentage given to them. And that should be all we need. So if I go ahead and run the game, let's run over to my switch. And I'm going to grab it and just pull it slightly and let go. It's going to go back. I'm going to pull it down halfway. Pull it down halfway. And as you can see, it stays there. It's not going to shoot up or shoot down. And then if I pull it down too far, probably right about there, yeah, it'll fully set off. So now our switches feel a little bit better, like that. So now that our switch feels a little bit better, let's talk about our wheel. Let's run over to our wheel here. And you'll see if I grab onto the wheel and turn it, it kind of just stops. That doesn't really feel how wheels work, right? You got to think maybe there's kind of a gear behind it and it's going to go doog, 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 and I let go and it's going to go and kind of snap back into place. That's kind of how I imagine most wheels working. And you could change the logic how you see fit, but we're going to make this wheel feel a little bit better by adding what I'm going to call kickback. So let's go into our interaction component again. Come up here, and wherever we had our switch variables, we're just going to add our wheel variables. And so we need a new variable. We're going to call it wheel kickback. Wheel kickback is a float, and we're just going to define it at 0.0 for now. And then we're going to add another variable, which we're going to call wheel kick intensity, which is also a float, and this is going to be 0.1. So this wheel kickback is going to be used in our calculation, and this wheel kick intensity defines how far back the wheel is going to kind of shimmy once you let go of it. So let's go ahead and start in our post interact down here. So here in our post interact, I don't actually think we need a post interact for the door. Let's go ahead and just remove that for the time being. Now, if we look at our wheel, we only need to affect one thing, and that's the wheel kickback. So the way we're going to do this is we're going to define the wheel kickback as being minus sign of wheel rotation times the kick intensity. And so what does sign mean? So sign just returns a value of 1 if the wheel rotation is positive. It's going to return a value of -1 if the wheel rotation is negative. And by saying minus sign, we're just taking the opposite. So if we are moving the wheel counterclockwise, use your big brain here, moving it counterclockwise, we want to figure that out, and then we want to set it in reverse by the wheel kick intensity. So if we're going clockwise, we want to kick back to the left. If we're going counterclockwise, we want to kick back to the right. And that's all we need to do in our post interact. So now when we let go, we once again need to make a modification to our process method so that way it affects the wheel even after we let go. So back up here in our wheel, the first thing we need to check is if the wheel kickback is going to be greater than 0.01 again. Once again, this is a threshold because we are lerping at the very end of the lerp. We just need to set it there so that way it's at a nice round number. So now we've just let go of the wheel and we need to start rotating. So we care about the wheel rotation and we want to add the wheel kickback to it. So remember, if the wheel kickback is negative, we will be subtracting the kickback off of this. So after we've affected the wheel rotation, we then want to take the kickback itself and we want to lerp from it back to 0. And then we want to do delta, and I think I'm just going to hard code this at 6 or something like that. So essentially, this is kind of abstracted 3 times. We have the actual rotation of the wheel being affected, then we have the internal wheel rotation that we are using to keep track of the wheel. Now the wheel kickback is going to affect the wheel rotation that is going to affect the wheel. Kind of confusing, but it allows us to do these nice smooth animations. And so that means that we're actually just going to be able to copy some of the logic from our wheel here. So the first thing we need to do is grab the logic that we use to ensure that the wheel rotation is being clamped correctly. So after we've correctly calculated the wheel kickback, we are going to want to set the wheel rotation and ensure that's clamped and not over kickback, you know, if it goes past the starting or the ending rotation. And then we also need to affect the actual rotation of the visible wheel to the player. So that's going to equal our wheel rotation, once again, times 0.1. And this logic is also held down below. We also need to calculate the percentage. So we need to calculate how far we've turned the wheel. And then we also, once again, need to notify the nodes with this given percentage. So let's go ahead and test and see what happens. Start the game. I will run over to our wheel. I'll turn it to the left, let go. It kind of kicks back a little bit. Turn it to the right, kicks back a little bit. That looks pretty good. It feels like we're moving over gears now. Now, one thing that might not make sense is typically you would only have this gear ratio working in one direction on a real machine. so you may not want it on the right. Maybe you want it to spin all the way and shoot back to the start. There's a lot of wheel logic you could do, but now you're starting to see the basis of how you would do it. Once you let go, you'd have some logic in the process function performing that rotation for you. So finally, we are going to add some meat and girth to our door. So let's go ahead and go back up to the start. We just added our door angle, so we're going to go ahead and add a little comment for more door variables. Now, all we really want to do is kind of simulate inertia for the door. For me personally, I don't want my door to actually behave as a physics body. If you wanted to, say, slam a box into your door to open it or do something of that nature, you could do a few things like changing your door to be a kinematic body 3D. You could also have collisions that would trigger certain behavior on it, kind of sitting just out of view of the door. But I don't really want that. I like having my doors as static and forcing the player to interact with them, because in the terms of a horror game, I think I could script kind of jump scares around that. So we're going to leave it as it is, but we are going to add some more variables. So the first thing we need to do is we need to keep track of our door's velocity, which is going to hold the speed of the door as it's moving. We're going to create a variable that I'm going to call door smoothing, which is a float. And this is kind of our important one. This is going to, I'm going to add a comment for this. This is going to control how heavy the door feels when opening and letting go. So this is something you can maybe even export, where if you have small wooden doors you want to be able to swing open like we have, but then you have big stone metal doors, maybe you want those to be a little heavier. So I'm going with 80. This is a very high number, kind of dramatic for the sake of the tutorial. And finally, similar to the switch is switch snapping, we want to check if the door input is active, and that's just a bool, which is going to start as a false. So this one's going to behave a little differently because we don't need to set anything for the door in the post interact. Instead, we are going to go down to our interact here on the door in our input function, and we're going to say that our door input is active. So this is just saying we are currently interacting with the door. And so we are going to modify this one more time. In this situation, we no longer need to be manually rotating the door via its rotate Y function, because instead we're going to be applying a velocity to it. If you think about it, a open velocity and then a closing velocity. So we can go ahead and get rid of this. We still need to check if it's front or not. So we're just going to say if not front, then we want to switch the delta. So if we're grabbing the door from behind, then we want to change the angle. We then want to say if the absolute value of delta is less than 0.01, we want to say that it is multiplied by 0.25. And all this does, this simulates resistance to small little pushes. So let me go ahead, I guess I can't run it now. But if you imagine when you open a big heavy door, you kind of need to put some, like maybe push a shoulder into it to kind of get it started. And this is kind of simulate the inertia, right? So if you look at delta and it's less than 0.01, I've barely moved the mouse. The door really shouldn't move at all. Like I'm barely pushing on it with maybe a pinky finger. So we want to make sure that that resistance is felt on the door. And so now, instead of manually handling this rotation here, what we're actually going to do is just set the velocity at what the door should be moving at. So once again, we are going to use lerp to kind of animate this. So we're going to take the door velocity. We're going to lerp towards delta. So we're kind of going towards building up speed or going towards slowing down. And we are going to do this at the speed at the inverse of the door smoothing. And that's the reason we do that is because 1 over divided by, what did I say, 80? You know, 1/80th, that's a very, very small number. That's going to be very slow and clunky to open. Whereas if I did 1 over, you know, let's say 2, that's 0.5. That should be a very smooth resistance. And so now, instead of actually handling our door movement in the input, we are going to come up to our process function. And where our door is, here's where we're going to handle the velocity. So we're going to have our door angle, and that's going to be affected by our velocity. Remember, our door angle is just the manual way we are keeping track of rotation to remove negatives. We are going to essentially rewrite the logic we had before. And then once we have moved the door, we say that we are no longer interacting with the door, because that should be immediately updated on the very next frame as we are interacting with the door. So now we just need to handle the case that we have let go. So if we are no longer interacting with the door, then we want the door velocity to lerp from itself towards 0 at a rate of delta and let's say 4 or something like that. All right, so I believe I've made a mistake there. So what is this saying? So door velocity is not a typical velocity as you would define it in Godot. Velocity is rather just a certain large number that, or certain number that defines how much the door should be moving. So we're still manually calculating the angle of the door using this quote unquote velocity. The difference is now that we've kind of abstracted how fast or how slow the door is moving, we can then animate through that to change that speed. So let's go ahead and test and see what the door feels like. So if I run over to the door and I kind of knock my mouse back and forth, I wish I had a camera for my mouse to show this, but you can see the door is barely moving. And if you wanted this to feel very spooky, what you could do is you could play a sound effect as you let go to do some kind of creak. But I think that feels really good. Yeah, that feels like a big, heavy door. Let me just go ahead and be obnoxious with this. And let's change this to, where did I do this? Door 80, let's make it 800. Let's make this a big, heavy door. So if I grab this and I push, oh yeah, that feels heavy. Look at that. That barely moves. And let's go ahead and just set this to something like 1, see what that looks like. And we push, and you can see there's no inertia on it at all. You see a big door, there you go. That feels pretty good. And so let's go ahead and talk about that last little flip here. So there is something I have felt as I'm pushing my mouse forward and I let go. You can see my camera shoots very, very high up. If I'm spinning the wheel and I go let go, my camera kind of shoots out to the side there. I don't know if you guys have noticed that, but it does feel very clunky. So let's go ahead and actually go back into our player script and kind of add some more sensitivity settings to make this feel a little bit better. So down here we had our base field of view and our mouse sensitivity. I'm going to go ahead and call this our normal sensitivity because that's what it should be at any other point in the game. And we're going to, once again, lerp through kind of a slow sensitivity to a fast sensitivity when we're letting go of something. And this will make more sense when it's done. So we care about the normal sensitivity and we want the current sensitivity, which is going to allow us to lerp through things. And we want that equal to, just this is fine. Let's see here. We want our sensitivity to have a restore speed, which is going to be how fast we go back to being normal again. 5 feels like a good value. And then we want a Boolean to see if we should be fading our sensitivity or not. So we're going to say sensitivity fading in. That's a Boolean, and that'll be false for now. And we'll just call this sensitivity settings. All right, so that's going to leave us with some bugs here for now, but just go ahead and copy your normal sensitivity in there, just like that, because what we're actually going to need to add is another process function. We did not use this before. We've been using the physics process this whole time. And we are going to handle our sensitivity change here. So let's go ahead and check if our sensitivity is fading in, meaning that we should be changing its speed. We want our current sensitivity to lerp between where we are now and go back to our normal sensitivity at a rate of delta times our restore speed. We also, once again, because we're lerping, we need to make sure that we're kind of setting the sensitivity back once we're close enough to a given threshold, which I find 0.01 to be a good one. So if we've lerped for a while and we're pretty close, we're just going to go ahead and set that back to our normal sensitivity, and we are no longer fading our sensitivity in. So now, instead of just having the camera either locked or if the camera is unlocked, we've added in this little transition period here where the camera was locked, but now we don't want to immediately go back to 100% sensitivity. We want to fade into it. So we need to add a little bit extra logic. So what we actually need to do is down here, add a function. We're going to call this set camera locked. And we are going to send in this value ourselves as an argument. Like this. And so we care if the camera's locked, then we want our current sensitivity to just be nothing, right? And then, of course, the sensitivity fading in is false because we're not actually modifying our camera. If it's not locked, then we just want to say that this is true. So now we need to call this. And so we're going to call this back up where we were just modifying that logic in our process function here. So if our sensitivity is not necessarily fading in, what we want to do is we want to set camera locked, and we only want to know if, according to our interaction controller, our camera is locked. So let's go back to this logic one more time. So this process on the player script is running every single frame, and it's going to check if sensitivity is fading in. If it is, we're going to do our new logic, but let's say we're not. Let's say we have just locked the camera, right? So at the end of that frame, we have just clicked on the wheel and are spinning it. It's going to tell the camera, hey, call the interaction controller and find out if the camera is locked. The interaction controller is going to say, hey, are we interacting with the wheel? And if the wheel is the wheel defined as locking the camera? In our case, the wheel is, so that will return true. If we go back to our player script, we'll set the camera locked to be true. And down here, this will be true. So if true, we've now set our sensitivity to 0 and we're not fading in. However, at some point back here in our process function, we will let go of that wheel, and the frame that we let go of the wheel, interaction controller.isCameraLocked will become false. So at the end of this frame, we'll set the camera lock to be false. And if it's false, we'll say that we should start fading back into our sensitivity. So on the frame after that, we are now fading in, and we're going to begin to update our sensitivity from our current, which is 0, back to our normal sensitivity, which is 0.2. And that's going to happen frame over frame over frame. Let's say it happens over 10 frames. And on the 11th frame, we're going to say, are we still fading in? Yes, we are, but we've reached the threshold where our current sensitivity is 1/100th or less. I think that's how I should say that. 1/100th or less away from our normal sensitivity. So we're just going to set it back to normal and finish fading in. So now that we've stopped interacting with the wheel, we've updated our sensitivity to be nice and slow. We're going to go back to the next frame and say, are we interacting with anything yet? And before we test, we need to add one more addition to where we are actually modifying our camera. So as you can see, none of this logic is actually going to matter any, because in this case, we are only checking if the camera is locked. We actually need to add another check. So we're going to say if our current sensitivity is greater than our threshold, which is 0.01, and not locked. So this is just saying we don't want to start moving the camera until we have some sensitivity to begin to do so. So if the camera isn't locked and we are now fading up so the camera can move a little bit, then we should allow the camera to move by its normal sensitivity. And this is wrong. I forgot we updated that. We want our current sensitivity to be updated. So if our current sensitivity is at 0.05, we want to move that frame by 0.05. If it next frame's at 0.1, then we want to move that frame by 0.1 all the way until we get back to our normal sensitivity of 0.2. So let's go ahead and test and see if that works. I look at the door, I let go, Oh yeah, that's smooth. Look at the door, let go, and I just go up barely a little bit. Let's go ahead and try that on the wheel. So I spin the wheel in one big rotation, and then I don't even move my camera. But look at that, it feels smooth when you let go too. Oh, that's wonderful. Let's go ahead and try the switch. So if I grab the switch and pull down, oh yes. All right, so for those of you who stuck around to the very end of the video, let's talk about that surprise. As of the posting of this video, this project is now being hosted on my GitHub page. So I will leave a link in the description below, or perhaps in a pinned comment. So you can always keep track with the most updated code, and I will try to update the GitHub with every additional tutorial video. So feel free to share that around and keep it posted. I don't believe I'm going to be making any more bug fix update videos. As I edit this, it's pretty clear that they take up a large chunk of time, and I just don't feel that they're very necessary once I hold a GitHub page, unless there's some kind of like major game-breaking bug, in which case I probably will make a video about it. But yeah, all bug fixes from now on will just be pushed to the GitHub, and I will only be doing videos on the new features. Speaking of the new features, I put out a poll on my YouTube channel to see what you guys wanted more. I put it out for a sanity system or adding in notes, logs, diaries, things of that nature. And it looks like the sanity system won, which I'm very happy about because I am very excited to build that. So that will be the next episode, and I hope you will stick around for that. If you're not subscribed, go ahead and hit that subscribe button so that way you are notified when that tutorial goes live. And if you have any questions, comments, concerns, you can go ahead and leave a comment down below or leave them on the GitHub page. I will be accepting push requests and other suggestions for the controller. Until then, I hope to see you in the next one.